Welcome back to module 16. In this module, we will continue the discussion on the attosecond charge migration. We have already pointed out that this is an advanced topic and there are perhaps many ways one can represent the advanced topic, and here we are representing, or we are presenting the most of our work which we do in Indian Institute of Science, and we are providing mostly our perspective to look at attosecond charge migration from a chemist point of view. What we have discussed so far is the meaning of attosecond time scale. It is 10 to the power minus 18 second, that is the time scale we are talking about, and we have already seen that in this time scale only electron density can change as a function of time. Nuclei, which is heavier mass, which is having heavier mass than electrons, nuclei do not have time to move in this time scale. And we have seen that mostly attosecond dynamics is not representing chemical dynamics, which is necessarily dynamics of nuclei or dynamics of the transition state. Attosecond dynamics is representing the dynamics of chemical bonding, which is nothing but time dependent change of electron density during the chemical bonding. And we have already shown that two different molecules, when they are bound together, I can take molecule A and molecule B, they are weakly bound together, and this bonding, this intermolecular bonding is called non-covalent bonding. And if we take two different molecules which are weakly bound together, then we can selectively ionize one of them. We can remove an electron from one molecule and we can try to monitor how the electron density getting reorganized or new non-covalent bonding interactions can be formed after the ionization of these two different molecules which are weakly bound. So, that is the strategy we used in the theoretical exploration of different aspects of attosecond charge migration. There are many information we have in our hand right now. Ionization of weakly bound clusters may enable us to capture dynamics of attosecond chemical bonding to monitor time dependent change of electron density. Electronic relaxation and exchange interactions both are going to contribute to the attosecond charge migration, and we have seen that there is an oscillation in the few hundred attosecond time scale. There is an oscillation of the charge density from one moiety to the another moiety, followed by the damping which occurs in the femtosecond time scale. Within 10 femtosecond, the charge oscillation will stop because of the vibrational motion before the ionization. So, these interesting informations are already evident from theoretical work. Next question is, how do we probe it? That is an important question, because any theory is based on certain approximation and we have to confirm within that approximation whether our predictions are right or wrong. So, with this idea we will move to the experimental part of the attosecond charge migration dynamics. The technique which we need to follow should be able to monitor the change of the electron density. So, let us say there is a process here where I have two dissimilar molecules, A, B molecules. They are weakly bound, very weakly bound species. They are attached together, but they are weakly bound. That is called non-covalent bond. Now, if I remove an electron from B, then what I create a whole charge which is missing electron charge, or whole charge I create in B. And due to this creation, the electron density which we had in A may change and it may so happen that finally the electron density may look like this. This is just an imagination. Due to this whole charge density, this electron density in A is changing, and if electron density is changing in A, then we have to probe it. So the technique which we would like to implement here in this discussion, and this change we know that is going to be several attosecond. So I should have an attosecond resolution in the experimental technique, as well as the technique should be sensitive enough to see the changes which is occurring in the electron density in this moiety. So going from this to this, there will be a change, and that change should be encoded in the experimental spectrum. Experimental spectrum should encode the change in electron density. That is very important, and the technique which one can employ is called high harmonic generation spectroscopy. High harmonic generation spectroscopy is a self-probing spectroscopy of electron density. What does it mean? It will be clarified very soon by taking the classical picture of high harmonic, semi-classical picture of high harmonic generation. High harmonic generation is an emission of high energy photon. So if I have, let's say, 800 nanometer light focused in a gaseous medium, this is a gaseous medium, let's say. In a gaseous medium, if we focus 800 nanometer light, then what happens, this 800 nanometer propagates like this, and at the same time we create a new light, and the light is in the X-ray regime, and this light is created in the X-ray regime. So this light is created due to HHG process. HHG process, what does it mean? The polarization, we have discussed the polarization of a system, polarization Pn. That polarization depends on the electric field, input electric field plus input electric field square plus input electric field cube plus input electric field 4, like this it continues. That's the nonlinear polarization we have discussed. Now this linear term does not exist in the nonlinear polarization, so I'll remove this one. Only nonlinear polarization which is contributed by this higher order terms. And this input electric field is the field of the input beam, the fundamental beam, which is focused to the gaseous medium. When it is focused to the gaseous medium, then what I see is that all second harmonic, third harmonic, fourth harmonic, all these harmonics can be produced. Interestingly, we have seen that because this is an isotropic medium, the gaseous system is an isotropic medium, so odd harmonics are produced. So even harmonics are removed from this, and all odd harmonics are produced. So we get input to the power 5 plus all other harmonics, and this can be extended to the X-ray regime. So it's 800 nanometer pulse, center wavelength 800 nanometer pulse, which is having almost 1.5 eV photon energy, let's say, for the center wavelength. This can be converted to even 10 times or 100 times higher photon energy. So it can go up to XUV regime or X-ray regime. All these regimes can be produced with the help of this HHG process. Now in HHG process, as I told, that the 800 nanometer pulse is focused at a particular point, and the intensity at that focal point becomes much greater than 10 to the power 13 watt per centimeter square. So this is a huge intensity we use. This is a strong field effect which we have already discussed in the nonlinear optics. So in this strong field effect, due to this strong field effect, what happens, every molecule when this under the strong field, the molecules are ionized or atoms are ionized in the gaseous system. So if I consider that each atomic potential is like this, and electron is staying here only, this is electron atomic potential within atomic potential. Due to the strong field, this field is suppressed significantly, and due to this suppression, what happens, this electron tunnels out to the continuum, and which means that I ionize it. So the first step of high harmonic generation is the tunnel ionization, where electron is removed through the tunnel ionization process. Due to the barrier suppression, the barrier which is holding the electron to the atomic to the atom, that electron is removed from that. So it suddenly electron is free, and once an electron is free, what happens? So I have this is the point of focus, let's say, and the laser beam is going through like this way, and this is a gaseous medium. So I am picking up one molecule or one atomic response. So I have one atom here at this point. This atom will be ionized. So I have a free electron and the positively charged cation I have created. Now this free electron will experience this field only. This is the field is so strong, it is something like in a daylight we do not see stars. Does it mean that stars do not exist? They actually exist, but we don't see them because the sunlight is so powerful, so glowing, that we do not see the very thin light from stars. Similar, in taking that analogy, we can think about it. The beam which is passing through the atom is so strong field that the cationic field is not experienced by the electron anymore. Cation, as if cation doesn't exist anymore. So if I have free electron now, and if the electric field is propagating this way, then the field is changing along the perpendicular direction. So this is the propagation vector direction, and the field direction is this way. And we know that every half cycle field is changing. This finger is changing. It means that the force directions is changing. So what will happen? Electron will try to, so at this point electron I have produced, and that electron will try to go away from the from that point where it is produced, and then within half cycle the field has changed the direction to the opposite direction. So electron will come back. When it is coming back, there is a possibility that this electron can recollide with its parent cation, and that's called collision, acceleration and collision step. So tunnel ionization is the first step of removing an electron. Then acceleration is done by the field itself. Field is nothing but a force. So if a force is acting on a charged particle, that will be accelerated immediately, and that acceleration will not go along a particular direction. It will just change every half cycle. See, the field is changing the direction in every half cycle. So electron will try to go away from the cation and then come back to the cation, and when it's coming back, there is a possibility of recombination, and the possibility is very low. The probability of recombination is very low. But if they recombine, then what will happen? I will have an emission of the light, and that emission energy includes the IP, which is the binding energy of the electron. In order to remove an electron, I need to give the energy, but in order to recombine an electron with the cation, that energy will be released. That is called binding energy of the electron. So that binding energy will be released, plus the kinetic energy will be released, because electron was traveling in the field. So this travel has gained the kinetic energy for the electron, and then when it's recombining, when it's coming to a stop, then it will release the energy, and that energy content would include the binding energy of the electron and the kinetic energy which has been gained during this travel. So this is called three-step model. Now question is, we have to go back to the previous problem. Our problem is that there is a very fast time scale, and within this very fast time scale there is a change, and this is an artistic imagination. Let's say I have an electron density which is spherical like this, and that is becoming like a two lobes. Okay, this is just an imagination. So if there is a change of this kind of change in electron density, and within this attosecond time scale, if there is a change, then we have to understand that if the electron is recombining at this stage, the emission will be different. If the electron is recombining at this stage, emission will be different. So in HHG process, what is going on in HHG process, I have an electron I have removed. When I have removed an electron, the electron density was just like the sphere, okay, here. So I have removed an electron. The moment I have removed an electron, the electron density was like sphere. During the travel, when this electron was traveling in the field, when I have removed an electron, this was sphere, and then when it was traveling, this electron density is changing. And when after the change, when the electron is coming back and recolliding, it's seeing entirely different electron density. It's just like I have left home, seeing my daughter is doing something, and then when I came back, I see that my daughter is doing something else, and that change I'll be able to recognize. Similarly, an electron, when it's leaving the molecule, it's seeing one density and it left, and then when it was coming back and then recolliding, it has changed to another density. And the emission spectrum is very sensitive to the point of to the electron density which we have at the time of recollision. So if we need to employ, if we want to employ high harmonic generation spectroscopy in the attosecond dynamics, in probing attosecond dynamics, then the whole attention should be given in analyzing the spectrum and decoding the information of the change, because this change is coded in the spectrum or the emission, the emitted light. The emitted light, if we analyze it nicely, then this change will be encoded in that. So all we need to do is that we have to iterate the idea and then understand how that change was implemented in the spectrum, how to analyze the spectrum. Now, second question is that, okay, if this process, removing an electron and then recolliding with the same cation, how long does it take? Because we know that this process, this electron reorganization takes almost, let's say, 500 attosecond. So am I in that time scale? So let's say it is 500 attosecond. Within this 500 attosecond, can we recombine? This recombination time is actually 1.3 femtosecond. So we have pretty much the time scale which we need. So what will happen? During this removal, I remove an electron. This electron will travel for 1.3 femtosecond at the center wavelength 800 nanometer. So this time is 1.3 femtosecond. After 1.3 femtosecond, when electron is coming back, if there is a change in electron density, then the emission spectrum should encode the change of the electron density. So we have the time scale, necessary time scale, which is needed for attosecond dynamics, as well as through high harmonic generation, and we have also the recollision, this recombination step is actually sensitive to the electron density, current electron density which we have in the atom or molecule. That's why high harmonic generation spectroscopy is called self-probing spectroscopy, because it is using the probing scheme. It doesn't require, it is not like a pump probe spectroscopy. In pump probe spectroscopy, what we do, there is a pump which will create or excite the system to the excited state, and that system will be now evolving, and there will be a probe which will interrogate the system, how the system is evolving as a function of time. In a pump probe, I always need 2 pulses, but in HHG process, I need only 1 pulse, because I create the electron. That electron is a probe. It is coming back to probe the system at different time. So let's say instead of 800 nanometer, for 800 nanometer, my electron trajectory would be this much. But if I take 2000, let's say nanometer, 2000 nanometer, 2000 nanometer will have longer oscillation period, and that's why electron trajectory would be this much, this long. So, in one case I have this long trajectory, another case I have this long trajectory. What does it mean? I am asking the system to relax more. So, in this system has relaxed this much, so I can see this. But if I started with this, then system has relaxed a lot and then coming to recollision step. So, depending on what kind of central wavelength I can use, I can change the probing time, but it is a self-probing spectroscopy because electron is actually itself a probe for the HAG process. So, we use this HAG spectroscopic technique, and mostly, as I have told you, that when there is a when we focus the 800 nanometer pulse in this gas cell, I have to create a gas cell, and in the gas cell I have to focus the beam, and at the point where the focal point is there, I cannot use any window, because any window, every material will start absorbing above 200 nanometer. So, if it is greater than less than 200 nanometer, the wavelength less than 200 nanometer, every material will start absorbing. We do not have a good window for that. So, we have to use a hole so that light can pass through the hole, and then I can create the X-ray and then I can collect the X-ray. So, that's one important information we should remember, and this is the typical spectrum we see. What is the typical spectrum? This is the spectrum. So, what does it mean? It means that once I create this HAG, this blue light can be directed to a grating and CCD combination. This makes the spectrometer. In spectrometer, what we do, depending on the wavelength, we disperse the light, we disperse the color, and we detect what are the colors we have. And if we check the spectrum, then what we see is that this is the typical spectrum, and you see that 2n plus 1, this is the number which we are trying to give for the odd harmonics. All odd harmonics will be created. So, if 800 nanometer I consider to be omega naught, then I will create 3 omega naught, 5 omega naught, 7 omega naught, 9 omega naught, 11 omega naught, and so on. These are the odd harmonics we will always create. Odd harmonics are created in HAG process because the medium in which we create HAG is a gaseous medium, and any gaseous medium has isotropic property. What does it mean? Optical properties in this direction, 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 every direction optical properties are equivalent. But if I take a crystal, let us say solid state crystal, if I go this direction and if I go this direction, their properties can be different. It's more like if I go this direction, my spring more like this, and if I go another direction, then spring may be like this. It's something like that. So one can imagine that I have a medium with different springs in different direction. That is called an isotropic medium. But gaseous system, any gaseous phase is actually isotropic medium, and due to isotropic medium I have to maintain this centrosymmetry of the system, and that makes this odd harmonics generated. Now, in odd harmonics, so definitely this is going to be my 3 omega naught, this is going to be my 5 omega naught, this is going to be my 7 omega naught. So, up to 7 omega naught there is a sharp decay we see in the intensity. Then there is a plateau, there is no change of intensity, all these plateau are showing up, and then suddenly there will be a cutoff, there will be cutoff in this. And this is a typical spectrum. So, first what we will do in the spectrum, we will see a sharp decay in the intensity, then there will be a plateau, and then there will be a cutoff. So, this is a typical spectrum which we observe from the HAG process from any gaseous system. And we will go over the experimental setup to some extent which we have in Institute of Science. This is not the only way one can generate HAG. There are many other ways HAG can be generated. HAG can be generated in a false nozzle valve, in a false nozzle. HAG can be generated in a gas tube. So here we have used one gas cell. So what we have here, the first thing is the gas cell. This is the gas cell, and this is a schematic diagram, and the original diagram is here. So gas cell is actually attached to a XYZ translational stage, so that we can move the gas cell this way or that way, because I have two holes here. So one gas cell hole, and then another wall I have. In the wall I have one hole. So this hole and this hole has to be collinear, and that's why we have to use this XYZ translational state to adjust the position so that these two holes becomes collinear, so that the light can go through both holes. So I have the first gas cell, then second chamber, then third. So gas cell chamber, then chamber 1 and chamber 2. This chamber 1 and chamber 2, these are the we have used to for the differential pumping. Differential pumping is used to let's say I have a very high pressure in this regime. So there are chambers. Let's say one chamber. This is one chamber, then second chamber, then third chamber. There are three chambers I have. In the first chamber I have a hole, let's say, and in this chamber I have very high pressure. In the second chamber, that is there is a hole on this wall. So in the second chamber I again pump it down, and I have another hole here. So on both sides I have hole in the second chamber, and then third chamber I have hole here, but I have a big hollow tube here on this side. So what is going on, by taking these three chambers I can reduce the pressure step by step. So here in this gas cell pressure can be very high, can be few torr, let's say, but in this second chamber I have, let's say, minus 2 torr and 10 to the power minus 2 torr, and the third chamber I can create 10 to the power minus, let's say, 6 torr, and that's exactly shown here. So for in the first gas cell chamber is 30 torr, it could be, but then I reduce down the pressure to minus 1 and minus 6 as we move to the optics chamber. So why we need this vacuum? We need the vacuum because the energy of the XUV beam is very low, and an XUV is an ionizing radiation. Most of the VUV and XUV radiation which is coming from sun is absorbed by the upper atmosphere. It doesn't come to us, and if it is coming to us, we will not be able to survive. So XUV is absorbed by the atmospheric molecules, and that's exactly what we need to avoid here, because we want to get XUV. So in order to get XUV we have to create the vacuum, and in order to create, but XUV will be generated in the gas cell, but then the XUV beam has to be collected in the vacuum. So I have to have a transition from high pressure to the vacuum, and this transition is done with the help of this differential pumping, which is showing here the gradual decrease in the pressure. In the optics chamber, this is the high harmonic separation chamber or optics chamber. What we have used a silicon wafer. Two silicon wafers we have used. Silicon wafers are very interesting. Silicon is actually a semiconductor, and it has a band gap of almost 1.5 eV. So this 1.5 eV is comparable to the 800 nanometer energy, photon energy, and for the excitation for the high harmonic generation we are using 800 nanometer pulse. So what will happen, the silicon wafer will, when 800 nanometer is propagating like this way, it is reflected by this way, most of the 80% of the beam will be absorbed. What I am doing here is that once I have created HHG, both fundamental beam and the XUV beam are collinearly propagating. My task is to eliminate fundamental beam and only take XUV beam from it, and that's why two silicon wafers we use to reduce the 800 nanometer beam, as we show here with the help of colors, and then we use one aluminum filter. Why aluminum filter? Aluminum foil filter. We use aluminum foil at home all the time, but the thickness of aluminum foil which we use is probably 10 micron or 100 micron. But what we have used here is 0.6 micron, which is 600 nanometer, even less than the one which we use at home. So, what is the advantage of using an aluminum foil in the beam path is that we know that X-ray penetration depth is much larger than 800 or near IR. So, if I have a metal and if I use X-ray to go through it, it can actually penetrate through metal. But if I use 800 nanometer of visible light, or the light we have in this in the classroom, that light cannot penetrate to the metal, and we take that advantage because we have X-ray beam, XUV beam, and we have 800 nanometer beam. So, if I use aluminum foil, which is very thickness needs to be adjusted because thickness will cut down XUV beam as well. But if we adjust the thickness, for example, we are using 0.6 micron thick aluminum foil, that will allow my XUV beam to go through the foil. But 800 nanometer is now blocked at the aluminum foil, and because it is blocked, then we use a toroidal mirror. Toroidal mirror is nothing but a focusing mirror. What is focusing mirror? Why do we need focusing mirror? Because you see that the beam is focused here and slowly diverging here in this point, diverging, and all the beam is diverging actually. And in order to refocus the beam to the grating, I need a toroidal mirror. Toroidal mirror is actually nothing but a focusing mirror for the X-ray, and it is now directed to the grating, and grating is dispersing the beam. Grating equation, we have seen how grating can disperse the beam. We know that transmissive grating and reflective grating, both equations we have seen in the construction of ultra fast laser system. So, why we need to refocus the beam is because we are focusing the fundamental beam first at this point. So, every beam when we focus it first, it will be slowly diverging after the focus, and that is exactly going on with the XUV beam as well here, and this XUV beam needs to be refocused with the help of toroidal mirror. Toroidal mirror is nothing but a focusing mirror which will be directing the beam to the grating, and grating equation we have studied already in the construction of the ultra fast laser, which disperses the beam as a function of the incident angle, and finally the beam will be detected with the help of XUV CCD camera. CCD camera is very sensitive for detecting very low photon energy, and that we get low intensity light, so we can detect that one, and once we disperse it, we will be able to get the spectrum like this, what we have shown here. We will continue this session in the next lecture.